Hi everyone, my name is Cheng, and I work for SkyMeister Taiwan. The previous section talks about the graph level optimizations, which can be applied to any hardware. Now, we will get to the last part of our tutorial, hardware-dependent optimizations. In this section, we will use an example to demonstrate how to create an NvDLA-dependent optimization path in ONNC. And suppose we have an example model like the one in the slide. And we want to use NvDLA to run the inference with this model. This example contains 3 element-wise operators. There are more than one way to do the mapping. It's possible that we map a single operator into a single hardware operation, or a sequence of hardware operations. In this example, we will discuss 3 different mapping options and compare their performance later. Before we jump into the optimization details, I'd like to briefly talk about the SDP hardware block, which is the main component that carries out the model inference in this case. The diagram in the top right corner depicts the NvDLA architecture, where the SDP block handles most of the element-wise ONNC operators. If we look into the SDP block, we will see 3 major sub-blocks, X1, X2, and Y. X1 and X2 are identical blocks. Each of them contains an adder, a multiplier, and a ReLU unit. For this example, we can map the whole graph into the SDP block for execution. However, there are multiple mapping options. For example, if we map one operator at a time, we need 3 SDP operations to complete the inference. For this option, we need to move a tensor in and out of memory 6 times in total. It is simple and straightforward, but not efficient. And another option is to run the whole graph inference with a single SDP operation like option 2 in the slide. To do that, we need to map 3 element-wise operators into the X1 and X2 subblocks. In option 2, we cut down the execution time to 1/3 of the execution time in option 1. In addition, we only need to move a tensor in and out of memory twice. Furthermore, we can reorder the move and add operators to match the execution order of S1 block design for more efficient mapping. In option 3, we can carry out the inference using just a single S1 block for the whole graph. The previous 2 slides already explained how a better mapping is done. In order to implement a more efficient mapping, we need to transform the IR graph in 3 steps. First, ONNC initially converts the ONNC model into an ONNC IR graph. Next, we have to search for the move and add pattern and reorder them to match the execution order of the SDP block design for more compact mapping. Last, after operator reordering, we need to do IR conversion to fuse Add, Mul, and Relu into a single compound IR for more efficient mapping. Let's look at the reordering details. The basic idea behind the optimization is as follows. The original equation does a multiplication first and then followed by an addition. With proper mathematical transformation, we can do the other way around. Do the addition first and then followed by a multiplication. Note that we need to adjust the constant carefully, such that the result will remain the same. There are two preconditions to meet in order to have a valid conversion in this case. First, the output tensor of the add operator can only have one consumer. Second, the values of alpha and beta need to be determined at compile time. The first requirement is due to the fact that the add output is sent to the multiplier directory, and there's no data path to save the add output to memory in the SDP design. So, if add have another consumer, we have no way to save the add output for another consumer with this optimization. The second requirement comes from the fact that gamma has to be determined at compile time because there's no divider available in the hardware. It usually implies that the values of alpha and beta are constant values in the given model. Here we come to the lab section. In this lab section, we will show how to create two hardware-dependent optimization passes described in earlier slides. The first pass deals with the operator reordering, and the second pass handles compound IR fusion. And we will introduce how these passes are carried out in the ONNC framework. Before we jump into the monetization passes, I'd like to recap how to set up the developed environment quickly. The ONNC project provides a Docker image for easy setup. You may clone the ONNC community Docker image from the Docker Hub first. You also need to clone the ONNC and the ONNC tutorial repositories from GitHub. Once you have the Docker image and the repositories ready, you can start a Docker container using the command in the slide. If you have any issues, you may refer to Lab 1 in our tutorial for more details. After we log in the Docker container, we can start to create a new backend, FooNvdla. The details are similar to what is done in previous lab, and we will skip them in this lab. You may create a new FooNvdla backend by following the example commands in this slide. After we create a new backend, we can add the operator reordering pass into this backend. We provide all of the related files in the ONNC tutorial repository. So you may just copy the related files to the ONNC target folder in the Docker container. Next, we will go through the workflow of setting up the new pass. There are 6 steps in this pass. First, we will traverse the ONNC IR graph and search for the more add patterns and reorder the patterns to add more pairs. Then, we have to prepare to iterate through the match patterns. The diagram at the right-hand side shows the IR graph of more add patterns. We will show the effect of each step on the IR graph in the next few slides. Next, we will remove all edges between more and add operators, and their producers as well as consumers. We will rebuild their edges later on. Then, we have to create the gamma tensor and its initializer for the mathematically equivalent formula. After we calculate the value of gamma tensor, we don't need beta tensor anymore. So, we have to remove the beta tensor from the IR graph. The last step is to reconnect all of the operators and tensors. We will get the new AddMul sequence, like the diagram in the slide. After reordering the Mul-Add sequence, we need to fuse the Add-Mul-Relu operators to a new compound IR by the fusion path. Like the previous path, we provide all of the related files in the ONNC tutorial repository. Before we jump into the fusion path, we need to add the definition of a new compound IR and the other related files into the backend. The details about how to create a new IR are similar to what is done in previous lab. So, we will skip them by using the related files from ONNC tutorial repository. Here we will go through the fusion path. There are 5 steps in this path. First, we will traverse the ONNC IR graph and search for the Add-Mul-Relu pattern for layer fusion. The diagram on the right-hand side shows the IR graph of the Add-Mul-Relu pattern. We will show the effect of each step on the IR graph in the next few slides. Then, we have to prepare to iterate through the match patterns. We will create a new compound IR first. After creating a new compound IR, we will remove all the edges among the add, mul, and relu operators, and their producers as well as consumers. Then, we have to remove the add, mul, and relu operators and the activation tensors among these operators. The last step of this path is to connect a new compound IR and its input-output tensors. We will get a new IR graph like the one in the slide. After we add the reordering and the fusion passes to the backend, we need to modify the make files to compile the changes to the backend. Now, we are in the last step of this step. We can rebuild ONNC and compile the example model. If you compile successfully and run the inference, you will see the result of this lab like this slide. Thank you for joining us today. Welcome to try ONNC for your own project and post your questions in the ONNC community.